A digital computer has many combinational logic circuits. The main among them are the adder and the subtractor. In this presentation, we'll see the design and the implementation of the basic adder, the half adder circuit. Some specific combinational logic circuits are adders, subtractors, comparators, decoders, encoders, and multiplexers. Design a combinational logic circuit, the following steps should be followed. The first step is determine the required number of inputs and outputs. Assign a symbol to each. The next one, derive a truth table that defines the relationship between the inputs and the outputs. The third step is you get an expression from the truth table. You have to simplify that using any one of the methods. You can apply either the Boolean laws and the postulates, or you can make use of a Karnaugh map, Quine-McCluskey method, or any other suitable method. The last step is, after simplifying the expression, obtain the logic diagram and verify the correctness of the design. The inputs to the half adder are the addend and the organ, and the outputs from the adder are the sum and the carry. The half adder makes use of the following postulates: 0 plus 0 is 0, and all the remaining things are the same except for the last line. 1 plus 1 is equal to 1, 0. Now for the design of the half adder. The first step is the specification of the truth table. The truth table gives the relationship between the inputs, x and y in this case, and the outputs, c and s. Now to simplify the truth table, we'll have a look at all the rows of the truth table. First, have a look at the second row of the truth table. In the second row, the inputs x is equal to 0 and y is equal to 1. Look at the corresponding value of the output s. S is a 1. So if you want to form the SOP expression for s for the second row will be x bar y. Similarly, we'll try to decode the third row. The third row can similarly be decoded as x is 1, y is 0, and s is 1. So the value of s will be s is equal to x into y bar. So to obtain the sum of products expression for s, obtain the rows of s for which it is 1. It is obvious that s is 1 only on row 2 and row 3. Taking all those expressions and combining, we get the expression for s as s is equal to x bar y plus x y bar, which is also equal to x XORed with y. The expression for C can also be derived in the same way. Look at the rows of C. You can observe that only the last row of C has a value 1. So the corresponding value of x and y are x is 1 and y is 1, which makes the expression for C to be C is equal to x into y, which is equal to x bar plus y bar, the whole bar. The next step is the implementation of the Boolean expression. Sum is xy bar plus x bar y, and the carry is x into y. Sum, as I said in the previous slide, can also be expressed as x XORed with y. So the sum expression is implemented using an XOR gate and a carry expression using the AND gate. We have come to the end of this presentation. In the next presentation, we'll see in detail about the full adder. Thank you.